So let's start into the calculations then for this experiment. So again, if we look at the details that we've got here, all our details are here. We've got 100 centimeter cubed of water. The sodium thiosulfate was that concentration. The average titration was 5.7. That means it needed 5.7 of sodium thiosulfate. So let's have a look at the calculations. M1V1, as usual, we have our iodine on the left and our thiosulfate on the right. So the one that we don't know is we don't know the concentration of the oxygen. That's the whole point of this experiment, to figure it out. So M1V1, and then you can see your N1 and your N2 is a 1:4 ratio, as we've just discussed. Your concentration is 0.02 of the thiosulfate, and the amount you used was 5.7 of the titration. So when you do the maths on that, you end up with M1 is equal to 0.00285 molar, and that's iodine. That's your concentration of your iodine. In other words, that's the concentration of your oxygen, because the more oxygen you had, the more iodine was produced. So we can change that from molar into moles in 1000 cm cubed, and we need this in parts per million. So we have it in moles per 1000 cm cubed, so we multiply next by the molecular mass of oxygen, which is 32 because it's O2, and that gets us 0.00912 grams in 1000 cm cubed. But we need milligrams in 1000 cm cubed, so you just multiply by 1000. And that gives us 9.12 milligrams in 1000 cm cubed. And you can convert that then straight away to 9.12 parts per million dissolved oxygen. So that's the basic layout of a question. Let's have a look at an exam question. This one is 2005. There's other ones, but we'll start with this one. So question 1, in an experiment to measure the concentration of dissolved oxygen in a river water sample, a bottle of water was filled from the river and it was analysed immediately. The experiment was carried out as follows. And then it goes through all the details, and you scan through this and see what it is you actually need. We have got a 50 cm cubed portion against a standard 0.01 thiosulfate, so you can see that. And it goes through actually the details of the experiment, which, again, you may not necessarily need. So let's look at the first question here, part A. Why was it necessary to analyse the sample of river water immediately? Well, because there is plant life in that river water, then it is going to photosynthesize. So we don't want the oxygen to increase. So don't want oxygen to increase. And you have to state the reason why. So increase due to photosynthesis. And again, you can write long sentences for this yourselves. In making the additions to the sample, why should the solutions used be concentrated? So when you add the solutions, in, because it's already full to the brim with water, naturally enough, if you add solutions in, it's going to displace some of the water, because there's no other room for it. If the solutions are concentrated, you're going to minimize the amount of water that's actually going to disappear off over the side of the bottle. So this particular one would be to minimize the amount of water. H2O, displaced, to use proper scientific terms, displaced over the edge of the bottle. Part C then. Describe how the additions of the concentrated solution of manganese 2 sulfate and the alkali potassium iodide to the bottle of river water should be carried out, and what essential precautions should be taken when replacing the stopper of the bottle after these additions. So this is worth 9 marks. So you're looking at a 6 and a 3 here, possibly 6 for the first one. So for this one here, what we would write is using a dropper or a pipette. So using a pipette under the level of the water. Under the level of the water. And that's enough. Using the pipette will get you 3 marks, and under the level of the water will give you another 3 marks. So that's the first part. And then the second part of the question, which starts here, what essential precautions should be taken when replacing the stopper of the bottle after these additions are made? And of course, is not to get any air in the bottle. Okay, so don't trap any air, because if you do, you're going to trap extra oxygen, and that's not what you want. Part D then, describe clearly the procedure for using a pipette to measure exactly 50 cm cubed portions of the iodine solution into the titration flask. And again, that's a standard experimental question. I'll let you answer that yourselves. It's fairly straightforward. What indicator is used in the titration? So this question here. So again, the indicator used is starch indicator. State when the indicator should be added to the titration flask and then describe the color change at the end point. So when should it be added? When your titration is at pale or straw, you'll often see is another term they put, pale or straw yellow. And then it's looking for the color change observed at the end point, and it's blue or black, blue-black, which is the way we describe it, to colorless. Again, colorless is the word you need, not clear. Part F then is just the calculations. The titration reaction describes the following equation. Let's go have a look at the calculations for this. So let's identify some of the details. So we've got 6 cm cubed. We've got a 0.1 molar sodium thiosulfate solution, and it's 50 cm cube portions of the iodine. And again, it's looking for us to calculate the concentration. So we're going to end up with molar here. So let's have a look at that. We're going to go with M1 V1 all over N1 equals M2 V2 over N2. We know straight away that if we're titrating the O2 against the S4O6 dinegative, then the ratio here is going to be 1:4. So N1 is equal to 1 and N2 is equal to 4, if you can remember that. Let's have a look at the molarity of the oxygen. Well, we don't know that because that's what we're trying to figure out. So that's M1. And then let's have a look at the volume of the iodine that's used. So we're dealing with 50 cm cubed portions of iodine. Remember, O2 is iodine in the question. And then we're looking for the molarity of the sodium thiosulfate. So the molarity is 0.01 and the amount of volume used was 6. That was your average titration. So now what you're going to do is work out M1 by bringing stuff across. So when you do the maths on that, that's going to give you 0.006. Oh, I think there's actually another 0 in there. I'm going to just check the calculator again. I think there is. So it's 3 zeros and a 6, which is 6 × 10⁻⁴. And again, that's your concentration. That is molar. Now this part F just asks us to calculate the concentration of the iodine solution in moles per litre. Moles per litre. So that's what molar is, moles per litre. If you want, you can write that as 0.0006 moles per litre. And then we move on to part G. It doesn't ask us to find in F any parts per million, but it does ask us to find it in part G. So in part G, for every 1 mole of oxygen gas in the water sample, 2 moles of iodine are liberated in this experiment, hence calculate the concentration of dissolved oxygen in the water sample. So let's have a look at part G. So our molarity of our iodine, as we've seen already, is 0.006. Oops, 006 moles per litre. Now, based on what it's told us in the question, for every 1 mole of oxygen, you get 2 moles of iodine. So that means oxygen is to iodine is a 1:2, or the reverse is true. So iodine to oxygen is going to be 2:1. So we have 0.006 moles per litre of iodine, which means therefore we have 0.0003 moles per litre of oxygen. Now again, we're looking for this in parts per million. So moles per litre is not good enough. So what we need to do is we need to multiply by the molecular weight of oxygen, which is 32. So you're going to multiply by 32. So multiplying that by 32 is going to give us 0.0096, and that's grams per litre. Again, we need parts per million, so we need milligrams per litre. So we're going to multiply by 1,000 to get milligrams per litre. So multiplying by 1,000, you end up with 9.6 milligrams per litre, which is equal to 9.6 parts per million. And that's essentially a leaving cert question with the maths involved in it.